welcome to the special edition presentation entitled Isotopes in Lichen for Geothermal Exploration. I'm Cameron Asher and I will guide you through this presentation. I'm going to start off by explaining what isotopes actually are, and then I'll move on to the problems and solutions I've had and my methodology of my research. So to start with, isotopes of a given element share the same number of protons but a different number of neutrons. So there's no charge deficit or positive. For example, carbon 12, 13 and 14. Carbon 12 has 6 protons, 6 neutrons. Carbon 13 has 6 protons, 7 neutrons, and carbon 14, 6 protons and 8 neutrons. So the only change is the neutrons. Isotopes of the same element can be measured as a ratio between the heavier and the lighter isotopes. So we can use this comparing it to a standard such as atmospheric nitrogen for nitrogen isotopes, which is constant around the world. We can compare our sample's isotope value to this atmospheric nitrogen value, and we can figure out if our sample is more enriched or less enriched in the heavier isotope. So the ratio of nitrogen in the atmosphere, atmospheric nitrogen, has a ratio of 0.0036765. So that's the ratio of carbon 15 to 14. So there's very little nitrogen 15 compared to nitrogen 14. Some isotopes are radioactive, most of them are stable. The ones I'm concerned with are only stable isotopes, carbon and nitrogen. So just again with carbon 14, 13 and 12, carbon 14 is radioactive, but carbon 13 and 12 are both stable. And as I said before, all isotopes have the same charge. It's only the neutrons that change. Because of the different amount of neutrons, each isotope has a different weight. So these weights affect the way in which they react. It's harder to evaporate more heavier isotopes, easier to evaporate the lighter isotopes. When you're evaporating water, you're going to evaporate your steam into the more lighter isotopes. And this is known as fractionation. This is the process of fractionation. And continuing on, if we compare the nitrogen isotopes of our sample to the standard, then we can give it a value, as I said, in relation to the more heavier isotope. Less of the heavier isotope gives it a more negative value, so we'll get like isotope values of -15, -10, etc. And more of the heavy isotope means it's a more positive value. And this degree of fractionation, we can track it through different processes. So evaporation has a certain fractionation limit, so it'll change the way in which these isotopes become more positive or less positive. So we can say, okay, if we've got a sample of positive 10, then we can track and find out which processes are responsible for giving it such a positive fractionation. So yeah, we can trace these, and it's known as a forensic tool. Our source is geothermal water, and our sample is lichen. So the only processes we're concerned with are the fractionation in the atmosphere. So when it goes from the geothermal water to the atmosphere, there's a fractionation. It becomes more negative. When the nitrogen goes from the atmosphere to the lichen, it becomes more negative again. So we've got 2 fractionation steps, making for very negative nitrogen isotopes. So going on to my actual thesis now. This slide pretty much sums up my whole presentation. So we've got the source is your magmatic or your heat source of a geothermal area. These heat source is giving out fluids, really rich in silica with a bit of nitrogen, carbon dioxide, sulfur, etc. This is travelling up through the ground and coming out of our geothermal pools. From here, it fractionates into the atmosphere, travels through the atmosphere, and whatever happens to the atmosphere changes it. So it may, from the nitrogen that comes out of the pool, may turn into ammonia. That ammonia may turn into ammonium, a solid. And eventually that'll come all the way over to our tree. We've got a nice little lichen, and the lichen absorbs the nitrogen, or the carbon. So the null hypothesis, we're aiming to disprove the null hypothesis. And the null hypothesis is that the geothermal isotopes in lichen are different to the non-geothermal isotopes in lichen. So So we want to examine areas within geothermal areas and outside of geothermal areas to find out if the isotopes are different. And at the end of the thesis, this is what I aim to present, is some kind of isoscape showing changes in isotopic value as a contour map. Obviously this isn't my sample site, I'm not using the Americas. And so why do we choose lichen? Lichen are perfect bioindicators. So a bioindicator is something we can use to track atmospheric pollution. In our case, we treat the geothermal gases as atmospheric pollution. So you don't need to read all of this, but the main things we want to find in our lichen is that lichen that have wide geothermal distribution are abundant, representative of the collection area, and they're easy to collect. Those are the three main factors that we're looking for in a lichen. So now we have to go and find a lichen that we can use that is pretty much everywhere. And of course lichen are available all year round. So we start off with our South Island transit. So originally we did a transit from Christchurch to Grandard, looking at all the species across the South Island, and eventually we came up with 4 species that are reasonably common across the width of the South Island. Xanthoria, Ramalina, Usnea, Stereochord. So these aren't actually species, they're genera, but I'll refer to them as species just because it's easier. And so we can see that they cover the whole South Island, but there's a lot of holes within this data. We need to find something that's more representative of the whole width. And so I went out and did another transect with a lot more sites and a lot more detailed investigation, and we found that Usnea covers pretty much the whole of the South Island minus these 2 bars. So what I want to do when I've got an area where one species doesn't cover, I want to find another species that does cover that area and the area of the original species, so I can say, hey, if one species is absent, can I use another species to represent that value that should be there if that species was existing? So the 3 species I chose eventually were Usnea, so it's fruticose, so it sticks up from the substrate like kind of like a bush. Cylindrical strands, so they're perfectly cylindrical strands rather than flat as in the next species. And it's common in almost every environment, although it does prefer more direct sunlight. And it's referred to as old man's beard, as shown by this photo of me with a nice beard of lichen. The other species we used were Ramalina. So it's fruticose, similar to the Usnea, it's bushy kind of lichen, except it has flat branches rather than cylindrical branches. And it's got cup-like apothecia, so these things here are reproductive structures of the lichen. And it's more common in what I thought was more nutrient-rich environments, so areas where there's a lot of fertiliser, and they don't show up so much where Usnea, the first species, exists. The third species is Xanthoria, so it's folio, so instead of being fruticose, which is the bush, this one's folio, so it's flat, but it's not a crust. It's pretty distinctive in that it's sulphur yellow to orange coloured, and it's got the same apothecia that Ramalina has, except these ones are more distinct in that a lot brighter orange. It's more common in coastal environments, but it is pretty common across almost every environment. And this is showing Xanthoria growing on the centre within my geothermal site, showing how close it is to the actual geothermal source waters. So just above this picture there's a geothermal pool that's extruding water at about 80 degrees. And so this will be getting their nitrogen and carbon directly from those geothermal sources. My methodology is really simple, it's a very linear process. I don't have many deviations. First off, I find my lichen in the field, and then I identify it to make sure it's the lichen that I want, which is pretty easy with most species that I've used. I then bag and tag it, freeze it or chill it in the fridge in the lab. I then wash, dry, and then grind up the liquid nitrogen. Then dry again, and put it into little capsules for testing. Then my supervisor Travis comes along and he tests it up in the stable isotope machine. And then it's burned up in this little furnace here, which burns at about 1080 degrees. And that turns all of the sample into a gas, which then can then be tested by this machine. And then I get the final product, which is a huge spreadsheet of data, which I will likely spend the next few months going through. The results so far, so for the South Island transect, which I was talking about before when I found which species of lichen I wanted to use, we looked at 5 samples at each site, and each site was 5 kilometres from each other. So it made about 37 sites from Christchurch to the west coast. Scroll there. And so what we wanted to do was to find the expected range in a non-geothermal area. So we can see this is the carbon isotopes graph. So we can see Christchurch starting at the left, coming all the way across to Craner, or to the west coast. Sorry. These lines represent various landmarks that are along the transect. So Porter's Pass being right here, Cath, the field station, being here, the Umpers Pass village, and then the Kumara little township there. There's not really a nice trend across this whole graph. The only thing we can really take away from this is that there's huge variation. So, for example, this site here, there's variation that covers on the order of 2 per mil, which is really far too big. When the error is so large that all of these samples could be essentially the same value, because the error values here match up with these values, they kind of all could be the same thing. So we need to reduce that error, and we see this error again in the nitrogen isotopes. There's a slight downward trend as we get towards the west coast, which is expected, but the variation again is huge, especially for this one here, where it's got a variation of about 5 per mil. These isotope values are all in the negatives, so they've all got a huge depletion in the heavier isotope. If we go back to the start of the presentation. And again, huge variation. We want to reduce that. So the first thing I did to try and reduce that was to look at a single lichen sample and see if the variation that we're seeing is just because of the site on where on the thallus we've sampled. So to start with, I cut this up into 14 pieces and then tested each of the 14 groups twice. So the duplicate samples for each site. And we found that the variation wasn't too large. There was about 3 parts per mil, 3 per mil difference across the whole thallus, but that's mainly because of one outlier, this number 14. Everything else is really consistent. That doesn't explain why we've got such huge variation back on this graph. So that's not the reason. The second reason was asking whether or not the samples, if washing the samples would change the variability. The premise behind this is that nitrogen species that have not been absorbed by the lichen are sitting on top of the lichen, so you can imagine dust and stuff like that, and that's going to change the isotopic value. So by washing these samples and then testing unwashed versus washed samples, you came up with this graph. And again, this doesn't really explain why there's such high variation. We've got a few outliers that have huge changes after washing, so it starts. The start of the arrow is the washed sample, the end of the arrow is the unwashed sample. And like I said, there's 2 really high changes in isotope value, but most of these are really small and there's no general trend. So we can't really pinpoint this as the reason why there's high variation. Something that we haven't done yet, we have sampled, but we haven't tested the samples yet, is for the North Island transect. So this is the same thing as the South Island transect, only we want to find out what the expected range is inside of a geothermal area. And we're comparing values that we can see in the literature, namely Tozer et al. So the sample sites, not so easy to see with this map. If you go to Google Earth, so each of these green dots represents a site in which samples were taken. So I did 2 transects here, a north-south and an east-west. So the east-west transect started in the Te Urarua National Park, went up across through Rotorua all the way up to Hamilton. The north-south started in Rotorua and went down past Taupo to the base of Lake Taupo. The values from the literature, Tozer et al., he was concerned with between Rotorua and Hamilton, and he got really negative isotope values. So these are his values plotted against my South Island values. His values are a lot more depleted in that heavier isotope of nitrogen. So we want to find out, is that normal? In the South Island, no, that's definitely not normal. But in the North Island, maybe that's different. We want to see if that's a geothermal influence that's giving it such a negative value. So the site in which we sampled is known as Ngātamariki. So it's a geothermal plant just north of Taupo. I'll just bring it up on here. And each of these green dots represents the site in which I sampled. Let's get rid of all these. So, as you can see, it's just north of Taupo, Taupo being down here. So that each of these green points where I sampled, and it covers the whole of the geothermal area. If we zoom in a bit more, not too much. We can see that it covers mostly forested and farmland areas. So there's two main land uses here, which may influence the isotope values that we will get when we test the samples. So the geothermal boundary is roughly in this kind of area here, and the two geothermal pools are centered where there's a lot of samples to be taken. So we want a really high spatial resolution. We've tested samples all the way outside of the geothermal area, so all the way out north, all the way out south, and to the west. And we want to find out, hopefully we get samples that are something like this. There's some kind of influence from the land use, but the main influence is from the isotopes and the geothermal pools. So essentially, we want to find out if there's a difference or not between values of lichen in the geothermal area and outside of the geothermal area. And we've analysed lichen across the South Island and the North Island, as well as the high spatial resolution of lichen within a geothermal system. And this is a multidisciplinary approach to developing a geothermal research tool. Hopefully we can use that to find more geothermal areas in the future. So thank you for listening. That's been my presentation.